Hi everybody, welcome to an abbreviated lecture section today. What I'd like us to talk about in sort of building on what we talked about last time is how does either a concentrated base / nucleophile, what we call the attacking species, change the rate of a reaction of elimination. So we talked about this with substitution, specifically that a strong nucleophile and a high concentration of that strong nucleophile winds up leading to an increase of rate in an SN2 reaction, while there's no change in the rate of an SN1 reaction. But how does this translate to the elimination side of the equation? And so what I'd like us to think about here is that, remember, we've got two unique mechanisms for elimination. E1, which is a stepwise elimination, and E2, which is a concerted elimination, which means that everything happens at the same time. And so if we remember our rate laws here, the rate of elimination that's happening by E1 is going to equal some constant K times the concentration of our electrophile, which in this case is just our alkyl X group, meaning that it is an aliphatic carbon with a leaving group. On the other hand here, what we see is that for an E2 reaction, very similar to what we see with the SN2 reaction, we see a direct dependence on the rate with both the electrophile, so both this alkyl X or alkyl leaving group species, as well as the base. And so what this means is that high concentrations of base increase reaction rate. Additionally, what we can think about is because this is indicating that both the alkyl X group and the base are playing a direct role during or prior to the rate determining step, the strength of the base we use is also going to indicate how quickly our reaction happens. So a strong base will also increase rate. So just like we talked about with the SN2 reaction, what we can see is that in the case of an E2 reaction, while the concentration of base increasing rate really makes sense, the strength of the base really isn't necessarily explicitly talked about in this rate equation. And so for us to figure out how this winds up working, we are going to have to draw a reaction coordinate diagram. Okay. So to do this, I'm just going to turn the camera so we've got some more space. So, traditional reaction coordinate diagram, what I'd like us to think about is on the one axis, we'll have Gibbs free energy, or G, and on the other axis, what we're going to wind up having is our reaction progress. And so what I'd like us to think about is I'd like us to think about two different E2 reactions, so two different bimolecular or concerted eliminations, where what we're going to do is we're going to form the same product, but we're going to do so with different strengths of bases. And so the first reaction that we're going to be doing is we're going to be taking tert-butyl bromide, and we are going to be treating this with methanol. So last time we talked about what makes a good base / nucleophile, and in chapter 3 we did a really big sort of story on what makes a strong or a weak base. And we can see that methanol is really not what we would consider a strong base. It's neutrally charged and it's relatively happy with the electrons that it has. So it's not going to have that driving force to go out and share that with a proton. And so in this case, what we can envision is that we're going to go up over our activation energy hill and produce our products here of our alkene, our leaving group, and our protonated base. So in this case, this would be the oxonium ion formed with methanol. Okay, so just as with the SN2 reaction, we're now going to systematically change the strength of the base. And so what we'll do is we'll make this a better base slash nucleophile, so a stronger attacking species, by simply introducing a negative charge. So by instead of using methanol, we'll use sodium methoxide, so the negatively charged anion of methanol. And so what this will do is this is going to create a species which is less stable. When something is less stable, we think about this as being more reactive or higher in energy. So in this case, what we can see is that the NaOH means that our reactants are actually boosted up in energy relative to the reactants with the weaker base. And this just deals with the fact that sodium methoxide is going to be more reactive than methanol. This is going to go over a relatively similar transition state and lead to essentially the same products. What we can see happening in this case, though, is that the hill that our reactants have to climb to go over this transition state, so this delta G double dagger, is smaller in the case where we have a more reactive starting material. And if we compare this to the delta G double dagger for the weaker base, we can see that that winds up being smaller. The smaller the hill that you have to climb, the faster the reaction happens. And so let's think of a little bit of a summary here. So in summary, strong nucleophiles or bases are going to favor SN2 or E2 reactions. So we'll do that right here. Conversely, weak nucleophiles and bases favor SN1 or E1 reactions, not because we're making them go faster, but we're slowing down the competing E2 and SN2 reactions. Okay, so this is video 1 of this series. Stay tuned for video 2, where we're going to be talking about the concentration of attacking species affecting the rate of substitution versus elimination. Thanks a bunch.